In this podcast, we're going to take a look at homeostasis in terms of thermoregulation, osmoregulation, and secretion. In the podcast titled Homeostasis, I talked all about how humans maintain their thermal or internal body temperature through a negative feedback loop. So I won't go back into that here. And I also want to remind you in the podcast about gas exchange, I talked about a countercurrent exchange in the gills of fish with the water flowing in one direction and the blood flowing in the opposite direction. Well, this is another example of countercurrent exchange, but this is for thermoregulation. So let's take a look at this Canada goose's leg. So this is the goose leg, and down here would be the little goose foot. That's literally a terrible goose foot, but you get what I mean. Okay, so what's going to happen here is the artery that travels down the leg is going to move in the opposite direction of the vein. Makes sense? But these two vessels are going to be very closely connected. And the reason for this is that in the body of the goose is all the vital organs. So it's really important that we maintain the temperature of our core with all of our vital organs. All right, so as the blood moves out of that warm body and travels down to the foot, which, could be in frigid water or standing on ice, it's going to lose heat, okay? And it can lose heat to the external environment. But what the goose has here in this countercurrent exchange is this artery will actually pass heat off to the vein that's closely connected to it. So as the blood moves down, instead of losing its heat to the external environment, it's going to pass off to the vein, and then as the blood returns back, it will gather that heat and return back at almost the exact same temperature as it left. So therefore, the core of that goose will maintain its body temperature, and that's our second example of a countercurrent gas exchange. Osmoregulation is the regulation of water and solutes. So it's kind of balancing our amount of water and our amount of solutes. Now, not everyone spends time and energy osmoregulating. Osmoconformers, internal solutions match their external. Right? So this would be like squids or hydra or sea anemones. They don't need to do any kind of osmoregulation because their water concentration is the same inside as it is outside in the ocean. So very clearly, osmoconformers can only be saltwater organisms. Freshwater fish have the problem of too much water and not enough solutes. So they actively take in like salt ions through the gills, and they're not going to drink any water. And then they're going to excrete a large amount of urine, and that urine's going to be really diluted. Saltwater fish have the exact opposite problem. They have too little water and too much solute. So they're going to be constantly drinking in salt water, actively excreting salt from the gills, and making very little, very concentrated urine. That's how they osmoregulate. Now, land animals are at a constant disadvantage and are very capable of dehydrating. Obviously, our waterproof skin helps, but how we really osmoregulate is our kidney. So what we're going to talk about now is how we regulate how much water we keep in our bloodstream and how much we excrete by our kidneys. What we're looking at here is a portion of our kidney, but the main thing I want to talk to you about is the nephron. You have two kidneys, and each kidney has literally millions of nephrons, and this is the functioning unit of your kidney. So this is your renal cortex, and this is your renal medulla. Whenever you see the word renal, just think right away, kidney. Medulla means middle. So this would be like the outer portion of your kidney, and then this is going to the inner parts of your kidney. The renal artery will deliver blood into your kidney, and then that blood is going to be filtered out right here in what's called the Bowman's capsule. Once things leave the blood, it's called filtrate. And what the nephron's job is to make sure it takes everything it needs out of that filtrate and then keeps the stuff it doesn't need in the filtrate so it'll get excreted. Okay, before we dive into the kidney, we got to get some vocab words down here. All right, so what's going to happen is blood's going to flow from the renal artery into the Bowman's capsule, and everything's going to get filtered here according to size. So this ball of arteries right in here, capillaries is a better word, ball of capillaries, is called the glomerulus. And things are going to leave the glomerulus and flow into the Bowman's capsule by size. So this is like a window screen. As the wind blows through a window screen, anything little like pollen or dust particles can blow right in. It's filtered out by size, but large insects are kept out. Now this is where high blood pressure becomes an issue. So imagine the blood is getting pushed in here really hard from a lot of pressure. Well, what it can do is tear that screen. Just like if you whip a baseball at a window screen, you're going to break it and put a hole into it. And then big things can come in. So what we would look for high blood pressure would be like proteins in your urine, because those big molecules could escape through those holes you made in your screen by all that pressure. Anyway, once things leave from the glomerulus into the Bowman's capsule, it's now in a tubule. And the fluid within the tubule is called filtrate, because it left through filtration. When we discuss reabsorption, what we're saying is things leave the filtrate and go back into the blood. So reabsorption is from, let me rewrite that, is from filtrate to blood, or from tubule, to capillary. Secretion is the exact opposite. In secretion, what we're looking at here is things going from blood to filtrate. So we're like, oh, we don't want this, let's get rid of it. That's secretion. So we're moving things from the blood to the filtrate. Excretion means we don't want it. In excretion, I always think of exit. It's actually going to leave the body. It's going to go from the tubule and eventually make it to the bladder and then leave. So this is going to leave the body. It's important you get these vocab words down. Let's go ahead and jump into our nephron. Let's take a closer look at our nephron. So as we discussed earlier, blood is going to flow into the glomerulus right here, and things will be filtered by size. And once things leave the capillaries of the glomerulus and go into the Bowman's capsule, it's called filtrate. And what's going to happen is the filtrate is going to pass through the proximal means close, so the proximal tubule. It's going to go down through the loop of Henle where water will be reabsorbed. As it moves up through the loop of Henle, salt will be reabsorbed. It's then going to go through the distal tubule, okay, and then once it hits the collecting duct, it's going to leave as urine. Okay, in the proximal tubule, your kidney balances the pH of your blood, and it does this by reabsorbing bicarbonate and secreting hydrogen ions. So that will balance out the pH. It's also going to reabsorb any nutrients here. Glucose, anything like that will be taken out of that filtrate. We don't want to get rid of our glucose. We need that. And then any kind of drugs or anything like that can then be, toxins can be secreted at this point as well. So now let's talk about the loop of Henle and its main purpose of reabsorbing water. So again, the filtrate has moved through the proximal tubule, and now it's going to move into the loop of Henle. The numbers in the filtrate right here note the osmolarity. Remember, osmolarity, kind of a lack of a better description, is the amount of stuff in water. So the higher this number is, then the lower our water concentration is and the more solute. Also remember, out here we have a bunch of capillaries. So as things move out of that filtrate, a lot of it's going to get picked up by those capillaries and then put back into the blood. So essentially the body will be keeping whatever's moving out of the filtrate. Okay, so as the filtrate passes through the descending loop is only permeable to water. So water is going to diffuse passively from high to low concentration. And the deeper we dive into the medulla, the higher the solute concentration is going to be. And that's really important to make sure that water, even though it's in a lower concentration here in the tubule, keeps leaving. Okay, because we have a high osmolarity outside here, and water will keep diffusing out. Again, the descending tubule is only permeable to water, so only water can leave. Now, here's my counter current within the nephron. All right, so the filtrate went down this way. Now it's going to come up the ascending tubule, moving in the opposite direction. The ascending tubule is not permeable to water. The ascending tubule is going to make sure that the inner medulla and the cortex stays solute rich so that the water will continuously leave that descending tubule. Okay, so how is it going to do that? Well, it's going to do that by at first passively moving salt out and then actively moving salt out. And by doing this, you can see the osmolarity begins to decrease as it moves up. So that means the water concentration is higher because we're pumping that salt out. And then that salt is going to be all around here, making sure the water would continuously leave the descending tubule. Otherwise, you'd get to a point where the water would no longer be able to diffuse out. Okay, once we get to our collecting duct, that is going to become urine eventually. So if it passes out here, it's going to go to a ureter, to the bladder, and then, out through the urethra. And in the collecting duct, we're also going to continue to reabsorb water. We're going to do that passively. It's going to move from a high to low concentration. And to make sure that out here stays solute rich, to keep that water flowing out, we'll continue to pump out salt. All right, but look right here, we're pumping out urea. Now, urea is a waste product, and it's what makes like your urine yellow and your sweat yellow. And it comes from basically our ammonia waste. It's how we move that throughout our body because that's so toxic. And if you notice, we're taking it out of the filtrate and we're moving it here to the ascending tubule. Why would we ever want to take something so toxic out of our filtrate? Even though we put it right back into the ascending tubule, why are we doing that? That's how important it is to us that we reabsorb water. We've kind of moved all the salt we can at this point. So by putting it in that inner medulla, we're going to go ahead and up our solute concentration, which will lower the water, so the water will continue to move out of that collecting duct, and then give the chance for our body to pick that water back up. All right, now let's talk about your antidiuretic hormone. Your antidiuretic hormone, or ADH, it's made in the hypothalamus of the brain, and it's released by the pituitary gland. And what ADH does is it tells this collecting duct, okay, I need you to go ahead and reabsorb more water. Put that water back into the blood. So if your hypothalamus picks up that you're dehydrated, then it's going to increase the amount of ADH it sends, so you reabsorb more water, meaning you make less urine because you're keeping all that water in your bloodstream. And you would notice that because you'd make less urine and your urine would be yellow or really dark yellow depending on how dehydrated you are. Now, here's the deal. If you drink something caffeinated, alcohol can do this as well. You basically turn off your antidiuretic hormone. So in the morning when I drink my cup of coffee, that caffeine is turning off my ADH, which means the water's staying in my collecting duct and not being reabsorbed. So I'm quite literally getting dehydrated because I'm not pulling that water back into my bloodstream, but I'm creating quite a bit of urine and it's clear, so you don't think you're dehydrated, but you really are. So you have to be very careful with caffeinated beverages. And that's your nephron. Isn't it kind of an amazing thing? I always thought it was pretty cool.